Hello guys, welcome to your favorite YouTube channel, My Project Ideas, and most importantly, welcome to this amazing DSA course that we have in hold for you. Today's topic is rather very interesting, that is asymptotic notations. So without much delay, let's see what today's lecture is all about. Here we are. So what are asymptotic notations? Those are the mathematical tools to represent the time complexity of algorithms for the asymptotic analysis. So, asymptotic notations are basically the tools which shows the time complexity of algorithms for your asymptotic analysis. Sorry, let's make it full screen. Yeah. So the following three asymptotic notations are mostly used. I was always telling you about big O notation, and this is a time complexity. You have to measure the time complexity. There must be a question in your mind that how are we going to measure those time complexities? What are the tools? What is the criteria? What unit do we have? So today's lecture will answer all your questions. So stay tuned and listen carefully. There are three types of notations. One is theta notation, one is big O notation, and one is omega notation. Let's see. So, theta notation, it basically bounds a function from above and below. So, it defines the exact asymptotic behavior. It's important. So, what does a theta notation basically do? It will bound. That means your function will have a lower bound and an upper bound. So, your function will be restricted to a particular range. So, this will define the exact asymptotic behavior. What is the simple way to get the theta notation? Is to drop the lower order terms and ignore the leading constants. What does this mean? See, this here I have given you an example right here. So suppose the function is 3n cube plus 6n square plus 6000. So here you can write it as theta of n cube. So what you have done is you have basically gotten rid of all those constants like the 3, 6 and 6000 and the lower order terms. Here your maximum order term is n cube. So the n square term and the constant term are dropped off. So it becomes theta of n cube. Dropping lower order terms is always fine because there will be always a number n after which theta of n cube has higher values than theta of n square. What does this mean? Suppose the value of n is 2. So 2 square is 4 and 2 cube is 8. So if you are covering 8, so by default you are covering 4 irrespective of the constants involved. So that's why we always take the upper bound, the higher term. Upper bound will be a wrong thing. It's higher term actually. And the theta of g of n is equal to fn. And this is the formula. Okay. There exists, sorry, let's go to the previous slide. Yeah. So there exist positive constants C1, C2 and N0 such that your N0 will be less than equal to C1 into G and will be less than equal to Fn is less than equal to C2 into G of n for all n is greater than equal to N0. This is a typo here. This is, I guess, N0. Yeah, it's N0. Okay. It's not 0, it's N0. I'm sorry for the mistake. It's a typo. Then let's move to that slide where we were studying. Yeah. So what does the above definition means? If f of n is theta of g of n, then the value of fn will always lie between c1 of g of n and c2 of g of n. So your values should always lie between c1 of g of n and c2 of g of n for larger values of n, where n will be greater than or equal to n0. The definition of theta also requires that Fn must be non-negative. Important guys. It should be non-negative and the values must lie between C1 into G of n and C2 into G of n. This was written here in a functional format. This is the actual format of it. Got it? Clear? Next slide. So I told you theoretically. Now let's look at the graphical structure. See, the Fn lies between C1 of G of n and C2 of G of n. This is the function of Fn is equal to theta g of n. I hope you got this is n0, this is n. Clear? Next, big O notation. The big O notation defines an upper bound of an algorithm. So you get the restriction of the upper bound only. The lower bound is set free. So the function is bound only from the above. For example, consider the case of insertion sort. It's a sorting algorithm. It takes linear time in the best case and quadratic time in the worst case. So it's big O of n in the best case, and in the worst case it's big O of n square. So you can safely say that the insertion sort time complexity is big O of n square. Always, always, always take in consideration of the worst case. So you have to note that big O of n square also covers linear time. If we use big O notation to represent the time complexity of the insertion sort, we can have two statements for best and the worst case. Worst case time complexity, as told you before, is big O of n square, and best case time complexity is big O of n. Let's look at the statement that we have. So big O of g of n is equal to f of n such that there exist positive constants c and n0 or n0 such that, again a typo, this is n0 is less than or equal to fn is less than or equal to c into g of n for all n is greater than or equal to n0. Got it? Next, let's have a look at the graph. This is the graph. So the statements graph, corresponding graph is given here. Next, let's move to the next slide. What is omega notation? So just as big O notation provides an asymptotic upper bound, the omega notation provides an asymptotic lower bound. So here you have in hold of the lower bound. So the restriction is there on the lower bound, upper bound is set free. So omega notation can be useful when we have a lower bound on the time complexity, and omega notation is basically the least used notation among all three. Got it? For a given function g of n, we denote omega of g of n as this. There's a typo here also. This is n naught. Okay, so here you have in the omega notation, you basically have restriction or the lower bound. You have an asymptotic lower bound. In the big O notation, you have an asymptotic upper bound, and in theta, you have both the lower bounds and upper bound. Got it? Have a look at the graph. This is a graph. Don't worry, all these PPTs will be shared to you in the description. You can read it.